Okay, I think we're recording, but all right. How are you guys doing? Doing okay? Have you guys taken a look at the first homework yet? Okay. Have you guys started? And how's that going? All right. Okay, so let me just kind of talk about a few problems. Problem one is just a very simple Monte Carlo approach for estimating pi. It's going to be do a bad job of estimating pi. But basically, you draw a square, and then you draw a circle inside the square, and you're going to see what percentage of randomly selected points fall inside the circle. And that should give you a ratio between the area of the circle and the area of the square, right? So, because the area of the circle is pi r squared, okay? And the area of the square would be 4r squared, right? So you take the radius and you square it, and then the square is 4 times that, right? And so, if you have no idea what pi is, you can kind of try to get an estimate of the area of the circle by randomly selecting points and seeing which ones fall in the circle. And then you take the ratio between how many have fall in the square versus how many fall in the circle, and that's going to be that ratio will be 4 over pi, or pi over 4. Okay, and then you can get an estimate of pi that way. Okay, or I guess I'm sorry. In this case, it's not a circle inside Garden square, is it? It looks like a top half of a circle. Well, I don't remember. Okay, I think it's a circle inside a square. Okay, in problem 2, you create your own exponential function to generate random values from an exponential function, and at the end, I ask you guys to use the Kolmogorov-Smirnov test. Do you guys have familiarity with this test? Okay. I asked the TA to cover this test, the KS test, and then in problem 3 also the chi-squared test, so you guys have an idea. But the KS test is a way for you to compare if 2 samples come from the same distribution, or in our case, if a sample of data is coming from a reference distribution. Okay, and what it does is it compares the difference between the CDF, or really it's the and the empirical CDF. So, well, maybe I'll back up. Are you guys familiar with the empirical CDF? Okay, so the CDF is the cumulative distribution function, right? And then what the empirical CDF is an estimate of what the CDF should be, okay? And it's based on your sample, and basically, if you have 100 data points, your empirical CDF will be kind of like a staircase with 100 little steps, and one along the y-axis is the kind of the percentile. So the first data point, let's say it's -4, will form the first percentile, and then the next data point, if it's like -3.5, will form the second percentile, and then the next data point, if it's -2, will form the third percentile, so on and so forth. And if you got if your 50th data point, after you arrange them from least to greatest in your set of 100, your 50th data point, let's say it's 0.02, that will form the 50th percentile. Okay, and then you just keep going, and then your 100th data point will form basically the 100th percentile. And so it's going to be a graph between percentiles, which will range from 0 to 1, versus the actual values on the in the data set. Okay, and that will form an estimate of the CDF. Okay, that's your empirical CDF. And what the KS test, the Kolmogorov-Smirnov test, does is it says, okay, I've got the theoretic CDF, in here I've got my empirical CDF, and we want to make a comparison to see if the two line up. Okay, so here, let me just do something quick. So X will be 100 random normal points. Let me actually round these. We'll round these to 2 decimal places. Okay, so if I print out X, this is what I've got. Okay, and then basically I'll sort X from least to greatest. Okay, and then I'm going to basically plot the values XS against a sequence from basically 0.01 to 1 by equals 0.01. Okay, and this is basically what my empirical CDF looks like. Okay, I'm just plotting each of these things, and maybe I would do type equals L. Okay, and this is kind of, or generally when you create an empirical is it not? Okay. Okay, this is kind of what your empirical CDF looks like. It's a plot between the values in your data set versus the percentile, which will range from 0 to 1. Okay, R has a nice function that does it for you. You don't have to do any of this stuff. You just do eCDFX, and that will produce the empirical CDF. And all you do is you ask plot the empirical CDF, and this produces pretty much the same plot, except just with slightly different stylings. Okay, it puts little dots on. Maybe this is closer to yeah. Okay, so this is, they're pretty much the same, right? Okay, so this is, if you just ask R to create your empirical CDF, this is what you have, and you can superimpose this against the theoretic CDF. So in our case, what is the function that generates the theoretic CDF for the normal distribution? P-norm, right? So we would do P-norm, and let's basically go from -3 to 3. Oh, so actually, we need to have a sequence S, a sequence from -3 to 3 by equals 0.01. Okay. So these are this is what we have, and then we'll just ask P-norm of all of this stuff. Okay, so these are the theoretic percentiles, and then so I would just plot S against the P-norm of S. We'll do type equals L and color equals red. And let's add this to our plot. So instead of plot, I'm going to do lines. And so the red line represents the theoretic CDF, and the black dots is our empirical CDF. And we ask, does the theoretic and the empirical CDF, do they line up pretty closely? And it seems that they do. Okay, and then the KS test formalizes this, and basically we would take our data X and we ask it to compare against P-norm. And it says ties shouldn't be present in the KS test, but here we go. We have the one sample Kolmogorov-Smirnov test, and it gives us a p-value of about 34%, which says which basically says that the p-value here represents the probability that a random sample drawn from the specified distribution looks like our random sample. Okay, so basically, the KS test, and like all hypothesis tests, we are not able to prove the null hypothesis. We're not able to say that this is proof that our data comes from the normal distribution. But what it does say is that our data gives us no reason to doubt that it's coming from this distribution. Okay. Meanwhile, like if I generated data z from the exponential distribution, okay, this is what our data looks like, and I can ask, okay, let's plot the ECDF of z, okay, and it looks like this. And then if I impose this against the CDF of the normal distribution, okay, and we can see that this and this definitely do not. Let me just change the x limits to. So if I plot the normal CDF in red against the empirical CDF of our data coming from the exponential distribution, there is great mismatch, right? And then so if I run the Kolmogorov-Smirnov test here, using our data z versus asking to compare against the normal CDF, it gives me a p-value on the order of 0. And it says, if the data truly comes from the normal distribution, if we were to draw a random sample from the normal distribution, the probability of getting our data is practically 0, is what it's saying here, okay? But, you know, if I take our same data, but instead of using p-norm, let's do the exponential distribution. That's going from here, let me just plot this again. And this, okay, so here is our, let's do, okay, so there's our empirical CDF versus the theoretic CDF for the exponential distribution, and then we'll do exponential, and we'll pass the rate parameter 1, and here it gives us a p-value. Okay, it's giving me some errors here, or warning messages, but it gives me a p-value of about 40%. Okay, so again, so now it says, well, if the theoretic distribution is this red line, the empirical CDF, then not the empirical CDF, the exponential CDF, and our data is what shows up in the black dots, the empirical CDF. It says, you know, what's the probability of getting this? It says, you know, there's about a 40% probability of getting data that looks like this. Therefore, we don't have any reason to doubt that our data is coming from this specified distribution. Is that good? Does that make sense? Yes, question.
So on the video that you put at the very top of the homework about the KS test,
yeah,
it looks at the greatest distance between 2 points.
Correct.
Is there any reason why that's more beneficial than looking at any other
Yeah. I mean, you could devise another test that does something like that. I don't remember the math that supports the KS test, like where this p-value is coming from. Like if you asked me to calculate this by hand, I wouldn't be able to do it. I just know that this is the test that we kind of use to kind of compare either two samples or sample against a theoretic one. Yeah, it uses the greatest distance, I guess to I forget now, but yeah, I honestly can't remember the math that goes into the KS test. I just know that this is kind of what we use. There are other tests to see if a certain values come from a certain distribution, and one's specified for certain things, like the Shapiro-Wilk test is for the normal distribution and things like that. This has been a kind of a long-standing problem of, does our data come from the distribution that I'm expecting it to come from? And it's kind of hard. It's all we can do is give you answers like, I have no reason to doubt it, okay? And that's the best we can do. We can't ever say, yes, for sure it does. For the discrete distribution, I have you guys use the chi-squared test, chi-squared goodness of fit test. And are you guys familiar with that, the chi-squared goodness of fit test? Maybe, maybe not. Okay, so the Kolmogorov-Smirnov test, the KS test, is useful when you have a continuous distribution, and then we can use the chi-squared goodness of fit test for discrete distributions, okay? And the idea here is you basically, here, let's do, what are the size and probability? Okay, so R binom size equals, so let's say you flip 4 coins and each coin has a probability of 0.5, okay? Oops. And we'll call this X. All right, so we can do bar plot X. Nope, that's not what I want. Oh, table X. Okay. So if we tabulate X, it'll tell us we have 5 zeros, 26 ones, and 42s, and things like this, okay? And we can compare this to D binom from 0 through 5. Size equals 4, probability equals 0.5. Okay, and so according to the 0 through 4, according to the rules of probability, we should get 0 6 times, 1 25 times, 2 37.5 times, and stuff like that. Okay, and so the chi-squared goodness of fit test is you provide it your table versus the probabilities, I believe. Let me see if this is correct. Okay, and here it says the chi-squared approximation may be incorrect. Okay, and the reason for that is that well, probably because I only selected 100. If I did 1,000, then we wouldn't have this issue. Okay. Oh no, maybe I'm still. have to do 1,000 times this? Oh. Degrees of freedom is equal to 8. I should only have 3 degrees of freedom. Let me see. Oh, I'm sorry. I have to do probability equals this. It's been a while. Okay. Chi-squared test. Oh, P equals. Okay. That's what I need to do. Okay, so here we go. Here we go. This is what I wanted to do. Chi-squared test for given probabilities. That's what we want. Okay. Do the chi-squared test. Chi-squared test, goodness of fit test, for given probabilities. And basically, over here in table X, is you are providing it kind of the counts of each outcome. So here I did R binom 1,000 size 4 probability equals 0.5. This says flip a coin 4 times, count how many times it landed heads, right? So you flip the coin 4 times, maybe it lands heads 3 times and tails once, okay? And then we repeat this 1,000 times and I say keep track of everything, okay? And that's what X is, okay? So X says, okay, the very first time I did it, you got 1 head. The next time you did it, you got 0 heads. Then you got 2 heads, and so on and so forth, okay? Table X tabulates everything, so it's a little bit easier to read. And it says, okay, you got 0 65 times, and 1 239 times, etc., etc., etc. So this is what we get, okay? And then you can do a bar plot, and this will show you what we have. D binom, this is the theoretic probabilities, and what we want to do is we want to compare our results in the table versus these theoretic probabilities. And the chi-squared test can do this, but you do have to specify P equals, the probabilities that we're expecting is equal to these theoretic probabilities. Okay, and then when we do this, it tells us that if the true probabilities are defined by D binom, then the probability that by random chance we get something that looks like our data is around 93%, 94%. Okay. Now, when you do your test, you might run into a problem. So here's with 100, but let me just try it with something like 50. Okay. So when I reduce our sample size to 50, okay, it gives me a warning, right? And it says the chi-squared approximation may be incorrect. And the problem with this is that if I do 50 times D binom, so, taking a look at our theoretic probabilities, if I multiply this by 50, okay, then it says in 50 coin flips, I would expect to get, in 50 trials, I would expect the outcome of getting 0 heads. That would happen about 3 times, okay? And the chi-squared test, underneath it all, there is a central limit theorem which says that you need to have a big enough sample size. And it kind of translates to each category has to have at least a prediction of 5, okay? So having only 3 is going to cause some problems, some approximation problems. And so what you might have to do, and this can be a little bit tedious, is that, when you tabulate your X's, you might have to collapse the smaller categories. So instead of saying, it's like, instead of having the categories 0, 1, 2, 3, and 4, we might have to collapse the 0 and the 1 together. And we might have to collapse the 3 and the 4 together, okay? In that having a category for 0 all by itself is going to be too small. So it's not worth having its own category, if that makes sense. So it's kind of like having a catch-all other category, except here we're going to collapse this. So basically, I'm going to take y to be table x, right? Well, what is the output of a table anyway? Type of y is type of y is integer, and if we look at the attributes of y, is that it's an integer vector, but it comes with dimension names, okay? And that's what basically tells it to print out this way. So basically what we're going to do is we're going to just take, so if I print out this, I'm going to ask, we're going to just reassign the sum of y1 and y2, basically the first two columns, and assign that to y2, and then we will get rid of the first thing. Oops. Okay, so maybe I'm not allowed to do that. Okay, so I've done that. We got to get rid of this first column, and then the last one I also have to collapse. So y3 will be the sum of y3 and y4. Okay, so basically I've just oh shoot, I did this wrong. Okay, hang on, I gotta go back. Alright, so I gotta do the I see. Okay. So, all right, we're gonna into the one that is named 1, we're going to add up the one that's named 0 and the one that's named 1. Okay, so I have to put these things in quotes. Okay. And then into the box that's named 3, I have to put in the value for the box that's named 3 and the value for the box that's named 4. Okay. And then, there we go. And then we can delete so we're just going to take boxes 2, 3, and 4. So we'll do 2 through 4. Okay, so there we go. Now I can run the chi-squared goodness of fit test. But again, it's a little bit of a pain here. So d binom 0 through 4, size equals 4, probability equals 0.5. And I have to combine these also. So I'm going to just kind of do probabilities will be so I have to add these two together and add these two together. Okay, and now I can finally compare my counts versus the probabilities here. So I can do chi-squared test of my counts y versus p equals my probabilities, and then I no longer have the warning. All right. Again, the issue here is if one of the categories has too small of a probability, after doing a certain number of trials, you're getting an expected count that's smaller than 5. And in those cases, you have to collapse the categories and you have to collapse the corresponding probabilities as well. Okay. Are there questions on this? I think I'm recording video of this, so when you're doing your homework, you should be able to refer back to this, and you'll be doing something very similar. Okay, and I hope it makes sense what's going on. Okay, let me just see if there's other issues in the homework that I want to address. Okay, so we've got estimating pi, Kolmogorov-Smirnov test, chi-squared test. Okay, and then the rest comes from rejection sampling, which is what we're going to cover today. Okay, are there any questions before I move on? Any questions about inverse CDF method for generating random variables, or generating random samples of a random variable? Okay, and again, the big picture idea is that in Monte Carlo methods, we're trying to avoid having to do the complicated math of integration and stuff to get estimates of expected value or variance or things like that, but we're just going to take a random sample drawn from it and then get empirical estimates of those things. There's another method. So inverse CDF method is pretty great, but we have another method for generating random samples of random variables, and that is rejection sampling. Okay. This is okay, and so we can use this when finding the inverse CDF is difficult. Okay, so so for example, like the CDF of the normal distribution does not exist in closed form. And I guess for our purpose, we will start off with the uniform case of rejection sampling, and we will say we've got a PDF of sin x. Okay. Okay, so our first case this will be the this will be called a uniform proposal. And the way it works is we're going to say the PDF, our PDF that of interest is proportional to sine of x, and we're on the interval that x goes from 0 to pi. So we go from 0 to pi, and this is what it looks like, right? So this is our PDF. Now, in order for it to be a PDF, the integral of f of x over the domain must equal 1, right? Okay. The integral of the PDF must equal 1. Okay, so in this case, the PDF isn't just sine of x, but it's going to be sine of x multiplied by some constant. Okay, so that the whole thing integrates to 1. So that means, so we'll say, we'll let f of x equal some constant times the sine of x. Okay. So here I'm going to say the integral of c times sine of x dx from 0 to pi, this has to equal 1. So what I get is the constant times cosine of x from 0 to pi has to equal 1. So here I get c, and then cosine of x evaluated at pi and evaluated at 0, it gives me 1 minus a negative 1. So I get c times 2 is equal to 1, therefore c must equal 1/2. So our PDF is going to be 1/2 sine x. Did I do something wrong? Oh, yeah, you're right, sorry. Okay. C times negative cosine of x evaluated at pi is 1, and yeah, minus the negative 1. Yeah, okay. All right. So far, so good? Okay, so if we say this is my PDF, the PDF is 1/2 sine x, going from 0 to pi, then that works, okay? Because the whole thing now integrates to 1. So here we've got a PDF. F of x is equal to 1/2 sine x. Okay, so this is our target distribution. And you know, I mean, at this point, it's not very hard to do inverse CDF method here, but what we will do, so this is what we're going to do, is we are going to propose values here, okay? So so what we do is to generate a random sample from this distribution, we will, okay, we will propose values according to the uniform distribution. Okay, and this from 0 to pi. We will propose values according to the uniform distribution, and then we will accept. We will randomly accept it if it falls inside the inside the target PDF. Okay, so propose values according to the uniform distribution. Okay, and then we generate another value between 0 and 1. And then we accept the value, the proposed value, if it fits or if it falls in the PDF region, and then we discard values that do not fall in the region. Okay. So our PDF is 1/2 sine x, and then this blue, the blue is our proposal distribution, which is the uniform distribution from 0 to pi. Okay, and what is the functional form of this? So if we say our proposal distribution g of x, what is the equation that defines g of x? So the whole thing has to integrate to 1, right? And it's a constant because it's flat. So how tall does it have to be if the whole thing's going to integrate to 1? It's going to be 1 over pi, right? Because the length is pi, so its height has to be 1 over pi, and therefore the total area, pi times 1 over pi, will equal 1, right? So g of x is 1 over pi for x between 0 and pi. Okay, but technically there is a mismatch here. Okay, because what's the tallest value? What's the maximum value of 1/2 sine x? So sine of x has a max value of 1. So max value of our PDF has a height of 1 over 2. Okay. Meanwhile, the height of 1 over pi has a height of 1 over pi, right? And if we stop and think about it, it makes sense, because if they're both PDFs, they both have an area of 1, but obviously in our picture, the blue rectangle is bigger, has an area greater than that of the sign. So what we're actually doing is we have to we multiply the g of x so that we get this kind of picture, okay? And so so that it creates kind of the we want to call it an envelope that contains the target PDF, okay? So, so we want the max value of f of x to equal the max value of g of x multiplied by some constant m. Okay, so the max of f of x is 1/2. The max of g of x is 1/pi. Okay, so what do we have to do? We have to do 1/2 is going to equal 1/pi times some constant m. So what is the value of m? Okay, just do some simple math and you get pi over 2 is equal to m. All right, is that okay? So we have pi over 2 is equal to m, and this is how it's going to work. Is let me save this. All right, so we've got, so again, we propose x by sampling from the uniform. Zero to pi, okay? And then we generate a u from uniform 0 to 1, and then we will accept x if the u is less than or equal to f of x divided by m times g of x. Okay, so let me just kind of draw that picture again. So we're going from 0 to pi, okay? So when you have a uniform distribution, perhaps you generate a value like right here. Okay, so let's say we generate a value right here. So we propose, I don't know what this is, 0.1 or something like that, okay? Just a small value. Now, in our, according to the PDF, a value down here, let's come over here. So let's say this is 0.1, and according to our PDF, values like 0.1 should not appear very often in our sample, right? Because the PDF, the value of the PDF here is pretty low, okay? So the PDF says (0.1) should not appear often. Okay, but if it's uniform, 0.1 is just as likely to appear as pi over 2, like 1.5, okay? So 0.1, every single value between 0 and pi are equally likely to show up from the uniform proposal, right? So this says it shouldn't appear often, But a uniform proposal will propose 0.1 just as often as, 1.5 or other values. Okay, all of the values are equally likely. So to decide, what we're going to do is every time 0.1 is proposed, we're not going to accept it. Sometimes we're going to say, no, I don't want this. Okay? And the way we're going to decide whether or not to accept 0.1 is we look at the ratio between the height of the PDF here and the height of the proposal distribution after we've modified it, after we've multiplied it by the constant here, so that the whole thing, these should be touching here, but okay. So according to, at this thing, it says it looks like, I don't know, this is like 20% of the way up. Okay, I don't know, I'm just eyeballing this, and this isn't even an accurate picture, but this says, most of the time we generate a value of 0.1, we should probably reject it. Okay, so if it falls up here, we would reject it, and if it falls down here, then we accept it. Okay, so we accept 0.1 with probability. We do a sine of 0.1 divided by, okay, m we decided was pi over 2, and g of x, the density, is 1 over pi, the proposal distribution. So we accept this with the probability sine of 0.1 divided by 1 over 2. Okay? So according to my calculator, mode radians sine of 0.1. Okay, we would accept this with a probability of about 20%, 19.97. Okay. Okay, and so the way we accept this with probability 0.1997 is we just generate another uniform value between 0 and 1, and if that uniform value is smaller than 0.1997, we'll accept it, and if it's bigger than that, we'll reject it. Okay, and so this is the equivalent of throwing darts at the rectangle, and we only accept the darts that have landed inside the PDF. Okay, and then the other darts we throw away, and thus we will get darts that follow the distribution of the PDF rather than those that follow the uniform distribution. Does that make sense? So, so let me see if I could just write up a brief script. Wait, let me just make sure that this is not your homework problem. Oh, I guess it is part of it. Okay. All right, so this is a rejection sampling uniform case, uniform proposal. All right, so f will be our function of x, and it's basically 1/2 sine of x. Okay. And then G is a function, and that's it just does 1 over pi. So just G of 4. Okay. G of 0, F of okay. So there we go. And then we have okay, so now I'm going to do our proposed values will be we'll do 1,000 proposed values on the interval 0 to pi. Okay, so let's just create a histogram of our proposed values. Okay, so here we've got a histogram. So the values that we're proposing are uniformly distributed. Okay, we got 1,000 of these things. Now but we don't want to. Here, let me just do 10,000 just to kind of emphasize this. Okay, so we have this. I can probably do like 40 breaks, and we'll still get. Okay. So we're proposing a whole bunch of these values. Now what we want to do is we only want to accept with a certain ratio, right? So we'll do accepted. So here I'm proposing 40,000 values on the interval 0 to pi, okay? And then we'll call, we'll generate a bunch of u's, are uniform, and we want 40,000 of these values between the values 0 and 1, okay? And then we will accept if the u is less than the ratio between f and g. I got to multiply it by m. M is equal to, what is it? Pi over 2. So it ends up just being 1/2 on the bottom. So accepted is a vector of true and falses. Is this okay? What's happening here? And then so our resulting the result will be our proposed values, but we subset only those that have been accepted. All right, and let's take a look at the resulting histogram here. Okay, and this looks a lot like the desired PDF. Okay, does this make sense, what I just did here? So this is the target PDF. Okay, this is my proposal PDF. Okay, in this case it's a constant because because we use the uniform distribution. So when you're using the uniform distribution, the PDF is just a constant. Okay. We propose values according to the proposal PDF, which is, we're proposing values between 0 and pi. So here, let me just show you. So let's look at the first 4 values that we've proposed. So we proposed the value, 2.26, 0.073, 2.49, and 1.25. Okay. And then we look at the random U's that we generate. Okay. So this is the probability of, should we accept this value or not? Okay. And then we ask, okay, well, what is the F of the proposed values? Okay. And we ask, okay, is this the F of the proposed value? And we say, what is that divided by M times the what's that divided by our function here? Okay. So here we've got, this is whether or not we should accept it, and we compare that to our U's, our first 4 U values. Okay. And then we say, okay, well, is this smaller than these acceptance ratios? And it says they are. Okay. And because they are, these 4 values will get accepted. Okay. But later on, this may not always be true. Let's just try. Okay, and in this case, one of them was rejected. Okay, so if I say what was, proposed 41 through 44. Okay, so here it proposed 0.17, which might be somewhere around here, 0.17. And then when we asked, what's the ratio between the PDF and the thing, okay, it's something much 0.17, just coincidentally there. Okay, and then so we say, okay, well, what is should we accept it, yes or no? And according to these values that we generated by U, we did not accept them. Are there questions on this? Okay, maybe we'll try an example and just do this thing by hand, okay? Just to illustrate and make sure that we understand this, okay? And because I want to make sure you guys get it. Okay, so let's say okay, so let's just stick with the same example, okay? So f of x is 1/2 sine of x, okay? Do you guys just have a regular plain calculator? Okay, well, and then g of x, again, is uniform on the interval 0 to pi, okay? Which is equal to 1 over pi. And then m is equal to basically the max of f well, we want f of x, the max of f of x to equal m times the max of g of x, okay? So m equals max of f of x divided by max of g of x. So we have 1/2 divided by 1 over pi, and we have pi over 2. Okay. So somebody propose a value between 0 and pi. Okay, so somebody just throw something out there. 2. Okay, so we propose the value 2. Okay? And then somebody propose a value between 0 and 1. 0.7. Okay. It's actually not proposed, but just generate. Generate a value between 0 and 1. Okay? So this we propose 2, and our u will be 0.7. Okay. So the question is, do we accept 2 as a value that has been randomly generated from our PDF? Okay. Well, we look at our acceptance ratio is going to be f of x divided by m times g of x, which in this case is 1/2 sine of x divided by m times g of x. So we've got m is pi over 2 times g of x, which is 1 over pi. Okay, and so according to my calculator, 1/2 times the sine of 2, this number is 0.4546, and this number down here is 1/2, and so my acceptance ratio is 0.909. Okay. Is that okay? All right. And then the value u that I got, u is 0.7. U is less than my acceptance ratio. So that means we accept 2. We accept the value 2. Okay? How often will be u greater than the acceptance ratio? It'll be greater than it only about 9%. A little, because this is, we accept it about 91% of the time, which means we will reject it about 9% of the time. Okay? And if we look at our picture, we can see that if we look at how often values like this are proposed versus rejected, we can see, oh yeah, it doesn't happen all that often. Okay, so this is, we propose all of these values, okay, on a uniform interval, but then if we look at whether or not we should accept them or reject them, we can see that values in this region, they're not rejected very often. Okay, but out here they're rejected more, right? And so we end up accepting only those with a probability according to the PDF. All right, I hope that makes sense. because we're going to continue on. And where we're not using a uniform proposal anymore. We're going to have the general case. Okay, any questions? We're good? Okay, so that's with a uniform proposal distribution. We might have something where we don't have a uniform proposal, okay? And so this is the general case of rejection sampling. It's pretty much the same. It just maybe looks a little bit more complicated. Okay. Okay. So same big idea as before. And really the same steps, okay? So you have target PDF f of x and then you have a proposal PDF g of x, okay, and then you propose an x, well, and then you find m such that m times g of x is greater than f of x for all x, okay? Okay, and then so you have proposal value x generate Okay, so this is what we have, except before g of x was a constant because it was the uniform proposal, and now we can have something that's not uniform. Okay, so here's our example is we'll do a normal distribution, but we'll our target will be the folded normal, okay? Target distribution is the folded normal. Okay, so the normal distribution just looks like this, right? Okay, and its PDF is 1 over root 2 pi e to the negative z squared over 2. Okay, where z on the interval negative infinity to infinity. Okay, and then the folded normal is basically just the positive half. And so its PDF what will its PDF be? So this time we'll say over here we had f of, should be f of z. In this case, our domain of x goes from 0 to infinity. So f of x would be what? Yeah, it's the same thing, but it's going to be 2 times the PDF, okay, of the normal. 2 times this, e to the negative x squared over 2. Okay, does that make sense? So it's this part over here is exactly the same as before, but in order for the whole thing to integrate to 1, we have to make it twice as tall. Okay? All right, so in this case, can we use a uniform proposal distribution? A uniform proposal distribution will not work because it would require us to generate values uniformly between 0 and infinity, okay? Which is not possible because that means we would propose the value 1 just as often as we would propose the value 10 to the billion power, just as often as we would propose the value 10 to the, I don't know, an even bigger number, okay? Every single number between 0 and infinity would be proposed with equal likelihood, okay? And I, it's hard for me to imagine numbers bigger than, to be honest, harder than a billion, okay? But, we can't propose values between 0 and infinity with equal likelihood, okay? So a uniform proposal will not work because it requires us to propose values from 0 to infinity with equal likelihood. Now we could say, for all intents and purposes, let's just say the normal distribution ends at 6. Then it could be done, okay? But then you'll never generate a value bigger than 6, which may or may not be a desirable feature, okay? So instead, for proposal distribution, we just need a simple distribution that is easy for us to generate values from and shares the same domain from 0 to pi, okay? So did we learn a way, are we able to propose values from another distribution? What distribution did we cover on Tuesday? Yeah, we can use the exponential distribution. That's easy, right? So we can do proposal distribution is we can use the exponential distribution. The exponential distribution with lambda equal to 1, okay, would be g of x is lambda e to the negative lambda x, which in this case would just become e to the negative x. And we get something that looks like this, g of x, and x has the same domain of 0 to infinity. So great. Okay, so this could work. Okay, and so what this will look like now so I've got this. This is what we have. This is what we want. And our proposal will be will look something like this, okay? This is not quite right, but okay, so here we got the exponential, and we have to so this thing is m times g of x, so that the target PDF is always underneath, right? Okay, so we've got f of x is equal to 2 times 1 over root 2 pi e to the negative x squared over 2. And g of x is e to the negative x, okay? And we want m to be equal to the, the max value of f of x divided by g of x, okay? And so this is going to be the max value of x of 2 over root 2 pi e to the negative x squared over 2 divided by e to the negative x. And here I get 2 times 1 over root 2 pi, and these combine to e to the negative x squared over 2 minus x. Okay. And so the max of this function, sorry, this is not, I still need to write maximum, argmax x. Okay. So the max of this happens at the minimum of x squared over 2 minus x. Right? So if I do this, if I just do d dx of x squared over 2 minus x, this gives me x minus 1. So our minimum happens, minimum at x equals to 1. So m is going to be equal to just plugging 1 into here, which is on the order of 1.32. Okay, so that will be the value of m that I use here. Is that okay? So we had to figure out, because I'll show you what it looks like. If I plot f of x and if I plot g of x, then we'll see that, g of x dips below f of x. So we have to modify g of x so that it is always at least or greater than f of x. So if I can just reuse this code, really. Okay, so my f of x is, what is it? 2 times 1 divided by the square root of 2 times pi times e to the negative x squared over 2. This is my target PDF. And the g of x is e to the negative of negative x. Oops. Unexpected symbol f of x. Two times the square root, 1 over the square root of 2 pi times exp of negative x squared. Huh? Oh, because I didn't comment that out. Thank you. I'm like, what's going on here? Okay. And then so let's just say S is a sequence from 0 to 6, and then length out we'll do to 200. Okay, so let's just plot this. So plot S versus f of s. And then let's add lines S and G of S. You know, I should probably do this one plot first. Well, I don't know. Probably have to do them both. Okay, so we've got this, and what we need is we need the red line, the proposal, to always be taller than the target, right? So if I take g of s and I multiply it by 1.32, times this, and let's make this blue, okay, then we can see indeed it is always taller. Let's change the y limits equal to c 0 to 1.5. Okay, so if we do that, you know, if we just scale up the exponential so that it's always taller, then this can work. Is that okay? So all I've done is I've just multiplied our proposal g of x by some constant so that it's always taller than what we get. All right. So now so we propose values according to our proposal distribution, and let's just take a look at what that is. Let's do breaks equals 40. Okay, so when I propose a whole bunch of these values, I get something that looks like this, and okay, then we'll so we'll let m equals 1.32. I'm going to propose a bunch of random numbers. Okay, then we'll see if we accept them, yes or no, and then we'll subset, and let's just see if this looks like. That looks like half in the normal distribution. Okay. If I put it on here, whoops, oh, not y limbs. Breaks equals 40, x limb equals. So we have This is what we had. So if we looked at everything, this is all of the values we proposed. And then these are the ones that we accepted, okay? If I, let me just subset my proposed. Just to those of proposed that are less than 6, okay? Just so we can kind of compare these two. Okay, so this is the exponential distribution, and then if we and this is what we accepted. Okay, so this looks like the exponential distribution, and then when we use rejection sampling, accepting only those that fall within the ratio, we'll get something that looks a lot like the normal distribution, or at least the positive half of it. Is that okay? All right, and then how can we go from this back to the regular non-folded normal distribution? What can we do? We just say randomly assign half of these to be negative. So I could just do negative to be basically, we'll say U, R unif, we'll ask for, well actually let's see, what is the length of result? Okay, so there's 30,161. We just have to randomly assign half of these. So we'll just say R unif length of the result, and if that value is less than 0.5, make it negative, okay? And then so our full normal distribution, full normal will be result so if it's less than 0.5, then it'll be true or false. Okay, I should do so negative is a vector of true and falses. Okay, so we'll do a result of those that are negative will be, we'll multiply those by -1, and then we will tack on everything that's in full normal and the results that are not negative. Okay, so if I do this, then this should work. Oh wait, something did not end up quite right, did there? Okay, I have to subset that. Those that okay, what am I doing wrong here? Okay, there we go. You have to use the opposite, not the negative command. Okay, so there we go. And so that looks a lot like the like a normal distribution. And yeah, and then you can do like QQ norm. See if that looks reasonable. And it looks pretty good. So I would say this has worked. Okay, so again, this is a rejection sampling. The idea is you've got some kind of target PDF that you want, and then you have a proposal distribution that's easy to sample from. So either, in our cases, ones that are easy to sample from for us are the uniform distribution, and in this case we looked at the exponential distribution. Okay, there's a few things that we have to do, and that is, one of them is you have to modify your proposal distribution by some constant m so that the proposal distribution is always taller than your target PDF. And if it is, then you're good. And then you you propose values from the proposal distribution, and then you'll accept it according to the acceptance ratio. Okay. So I'll just kind of, so in this, for the general case, well, not the general case, sorry, folded normal. Propose values from the exponential distribution. Okay, which is g of x equal to e to the negative x. And then, we found m, which is around 1.32. And then we use the acceptance ratio. What's going on here? Which is f of x divided by m times g of x. Okay, and we accept a proposed value if u is less than f of x divided by m times g of x. Discard the rest. So the resulting sample will be drawn from the target PDF. Okay, there is this is also covered in the textbook, which I've linked to in the syllabus, and you can download as long as you're connected to the UCLA network. Okay, so this should be you'll have some exercises in the homework to kind of make sure you get this and you're able to implement it into the code. Okay, and you can always I don't want to just copy. I don't want to post the sample code I've written in class today, but it is in the lecture video, and so you can kind of look at it and use the lecture video as a guideline to help you get started. But I do want you to at least try to go through the effort of at least typing this out yourself, because if I post it, I know there's going to be a lot of copying and pasting and stuff. So at least try that out. Okay, we'll end here for today, and you guys have your first assignment due next week, or in a few days. So please be sure to work on that, and we'll see you guys on Tuesday. Have a good weekend.